Hi, I'm Frank Bergschneider, and this is my course project for image processing and computer vision at the University of Florida. For my project, I chose to do real-time object detection using the SURF algorithm. First, I'll demonstrate my project, and then afterwards, I will do a quick presentation of the concepts behind SURF. So, first of all, the object I chose to detect was a copy of digital image processing by Gonzalez and Woods. It's the course textbook. So, here is a grayscale image of the textbook, which I'll be using to detect in a webcam feed on my laptop. So here you can see the frame rates are quite a bit slower doing real-time object detection, but you can see that the book is being found. You can move it around a little bit, and at various places there's enough interest points detected to recognize the book successfully. At different scales, there's various probabilities that it will be correctly identified. So, but fairly close to the camera. It's fairly robust to rotation and scale and variance. So that's my demonstration. We'll move to the presentation now. So yeah, once again, I'm doing real-time object recognition using the SURF algorithm. So just a quick word about object recognition. With ever-increasing demand placed on smart devices and user interactivity, object recognition is a key technology to enabling smart interactive programs and devices. And object recognition is employed in a wide range of applications, from consumer products to industrial inspection. This project will cover the basics of object recognition and feature extraction using SURF. Feature detection and extraction matching will be explained, and different methods will be contrasted. There are a variety of approaches for real-time object recognition, and most strategies are very computationally expensive and thus not really suitable for real-time. The SURF algorithm is a computationally efficient algorithm that enables real-time detection. So the project was implemented in C++ using the OpenCV library and the Eclipse integrated development environment. The OpenCV library provides an open source and easy-to-use framework for implementing computer vision projects. The library provides APIs to camera frame grabbers, convenient image data structures, and implementations of many common image processing operations. So, as far as related work goes, SURF is really based on the scale invariant feature transformation as created by David Lowe. SURF is really just a improvement upon the SIFT algorithm in that it adds rotation and decreases the feature vector size. And of course, the most commonly used detector is probably the Harris corner detector. So they drove heavily on that. SURF is essentially a Hessian-based detector, which gives it the concept of automatic scale selection, and so we'll go into that later. Another big influence was the difference of Gaussian filters, which is an approximation of the Laplace of Gaussian filters, and also with other approximations, the integral image and box filtering approximations provide huge amounts of speed-ups for the algorithm and are really at the core of it, and we will see that in just a moment. So there's three general steps for object recognition. The first step is interest point detection. The second is interest point description or feature vector extraction. And the third is matching feature vectors between two images. So here's the pseudocode for the overall program. First, a training image is loaded as a grayscale image. The interest points are detected using an approximated Hessian detector. The approximated Hessian matrix is calculated for a subregion around each point in the image, and the determinant is calculated. A point is declared an interest point if its determinant is a local maximum. A descriptor is then calculated for each of the found interest points. The descriptors give orientation, scale, and intensity distribution information, and the descriptors act as the input into the matching algorithm. The extracted feature vector for each image is then matched to features in the next image. A camera frame is grabbed for the loop, and all three steps are done between the original query image and each training image. And each step has to be sufficiently fast for online applications. So the first step is interest point detection. The detection of interest points is based on approximating the determinant of the Hessian matrix, which that is used to create a blob map at different scales over the images. Blob structures are then marked where the determinant is the maximum. So the detector approximates the Hessian using box filters and integral images, and the Hessian is defined as the convolution of an image region at a given point with the second derivative of a Gaussian filter at a given scale given by sigma. So just here you can see just a representation of the integral image, which I'll talk about in just a moment. Here is the approximated Gaussian filter. Here you can see this is much simpler than this, which is the actual derivative of the Gaussian. So next, the real heart of the detection is the integral image. So here is a representation of the integral image. The integral image is basically a summation of all intensity values up to a given point. So the integral image value for point S here would be the sum of all values below the x and y coordinates of S. Similarly for P, the integral image value would be the sum of all values below the x and y coordinates for X. And so this allows for a simple evaluation of a summation of a rectangular area of images. So here, for this area, which we'll call B, once you have the integral image calculated, the sum of the intensities in this square area would simply be P minus plus S minus Q minus R. And so you can see that's a constant time summation operation, which comes in handy, as we'll see. So as I was saying, the Hessian is the convolution of an image region with the second derivative of a Gaussian filter, seen here. And so we can approximate the second derivative of the Gaussian with this box filter, which a representation is given here. So you can see that using the integral image, we can evaluate each one of these boxes in a constant time very quickly instead of having to calculate an n by n number of multiplications and addition. So here, this provides an order of magnitude lower calculation time than direct convolution with a second derivative Gaussian. So here we can say the box filter is given by a sum of intensities times a coefficient. So for this area, we would calculate the sum of the intensity and multiply by -2, and similarly for all these, and then add them up, and that would be our box filter in that direction. And so we can do this similarly for the y direction and the diagonal directions, and from that we can approximate the Hessian as this statement given here. So we can also analyze features at different scales. For instead of iteratively downsampling the image and filtering, the original scale image is filtered with a scaled up filter mask. This allows rapid computation of the Hessian detector at different scales and doesn't introduce aliasing because downsampling isn't performed. The scale of the filter mask is increased in octaves, which define the scale of the subsampled image on an image pyramid scale. And so typically 3 octaves are used. The first filter octave given by mask size of 9, 15, 21, 27, and increasing similarly for the second and third octaves. More filter octaves can be used, but the number of feature points drops with high octaves. So also local minima of the determinant of the detector are suppressed, and local maxima are declared interest points. And then the remaining points are interpolated between different scales. And here you can see a representative image of interest points found using the detector. And so here's some sample code, pseudocode, of the basic algorithm, and you can take a look at that. Okay, so once interest points have been detected, they're characterized using first-order Haar wavelets to extract intensity distribution and orientation information. First, a circular area around the interest point is set up, and then an orientation is assigned. Then a square area is aligned with that orientation, and a 64-dimensional feature vector is extracted for each interest point. So for rotation invariance, we need an orientation. This is accomplished by establishing a circular area around each interest point. The Haar wavelet response is calculated for each one of these and then smoothed with a Gaussian filter. The smooth wavelet pairs represent an XY pair. So here you can see a representation of the Haar wavelet filter. This would be in the X direction, this would be in the Y. So it's just a simple box filter, so we can take advantage of our integral image and box filter to calculate the wavelet response. So once we have orientation information for each of the subsections, we can sum the X and Y directions to give an overall orientation. So once we have the orientation, a square area around an interest point, say here, is established. This area is then split into 4x4 square sub-areas. Each of the subregions are further split into a 2x2 sub-area, and Haar wavelets are calculated in the X and Y direction for each one of these. Once these are all calculated, they're also smoothed with a interest point centered Gaussian. And we can denote these responses as dx, dy. And so for each of these 4x4 square sub-areas, a 4-dimensional feature vector is formed. And since there are a total of 16 sub-areas, the result is a 64-dimensional feature vector for each interest point. And so this is the form of each of the entries into the feature vector. So each of these are also normalized to unit magnitude. The feature vector description is robust to illumination and contrast bias, and most of the empirical parameters were determined experimentally. And so here's the pseudocode for the description algorithm. So once we have the feature vector descriptors have been extracted between the training image and a query image, the feature vectors are then matched between the images. So I've implemented a simple matching scheme It's based on k-nearest neighbors and actually an approximate version of k-nearest neighbors, which is included in the OpenCV library, the FAST library for approximated neighbors algorithm. This algorithm trades some loss in accuracy for fast matching of high-dimensional feature vectors, which we have. So the algorithm returns two nearest matches. With these two nearest matches, a simple distance ratio is applied to ensure that they were a good fit. The distance ratio between the two neighbors was determined to be 0.6. If this value was greater than this, then the first match was accepted as a good match. And also a simple threshold rule was established where we simply had to have more than m number of matches to declare that we had a suitable number of matches to declare the object was found. For this, we chose 8 good matches to be sufficient. So here we just have an example of the object found. We have digital image processing book in the top frame, and so we can see there's been a square drawn around it for ease of viewing. On the bottom frame we have a different book which is similar in color and has some features, but we can see that the object is not recognized here in this case. So some results. There were several parameters that had to be determined experimentally for this object recognition task. The main parameter that had the greatest influence was the threshold set for the determinant of the Hessian. A minimum threshold was used to determine the number of interest points found. And so the number of interest points dramatically decreased as the minimum determinant was increased. And so we can see here, that's presented right here. And because of the computationally intense nature of the problem, frame rate was limited to below 10 frames per second for most combinations. So in respect to computational speed, an optimum balance between the detector and descriptor computation was found to be around 200 interest points, which corresponds to a determinant of 4,500. While this threshold allowed for fast computation, object recognition was significantly decreased at a distance beyond a few inches. The best minimum determinant in terms of speed and recognition was found to be around 2,000. The distance ratio of the two nearest neighbors was determined to be 0.6, and a good number of matches for object detection was set to 8 good matches. This led to an average frame rate of approximately 2.9 frames per second. Another interesting result was that the probability of recognition was fairly constant with a fixed number of matches at a given distance. We would get more matches for a lower number of good matches, but this resulted in a large number of false alarms, which is non-optimal. And so the probability of correct detection was tested by placing the test object, the book, 18 inches away from the camera and allowing the algorithm to run while varying the number of good matches. I also tested the probability of recognition as a function of distance by moving the unrotated book 6 inches away from the camera at a time. And as we can see, object recognition decreases pretty rapidly with distance. So, in conclusion, the SURF algorithm was implemented and tested using the OpenCV library. The SURF algorithm is a computationally efficient and sufficiently fast algorithm for real-time object detection algorithms. The performance enhancement is obtained by approximating a series of computationally intensive tasks without major loss in accuracy and repeatability from the approximations. And the integral image and box filter approach yield huge performance improvements because of the constant time calculations regardless of image size or filter size to approximate the Hessian of the matrix. And so also the surf is very robust to scale change and rotation and noise compared to many other algorithms. Another interesting thought, which has been followed by many people, is that the algorithm is primed for parallel or GPU implementation, since the majority of the detection and description steps are separate from each other as far as detecting interest points in different parts of the image. And so this would be a good exercise to do, which I think I'll follow up on. Alright, and so that's my presentation. I will post links to the slides, program, and report in the comment box. Please feel free to contact me with any questions. Alright, thank you very much.